Okay, you guys, we're going to learn two things today. Number one, we're going to learn this conceptual thing about what happens to the spring constant when you cut a spring in half or double it in length or put a spring in parallel with an identical spring. And this is all conceptual stuff. I need to make sure you get exposed to this so you understand how springs really work. And then we're going to learn about spring potential energy. I'm probably just going to tell you what the formula is. I'll prove it to you tomorrow. So I'll just tell you the formula, then we'll do lots of conservation of energy problems utilizing spring potential energy. But first, what happens to a spring, what happens to the spring constant when you cut a spring in half? What happens to K when you cut a spring in half? Okay, so hey, let's say I have a spring. 1, 2, 3, 4, 6, 7, 8, 9, 10. And let's say my spring has 10 coils. And let's say further that the spring has a spring constant of 20 newtons per meter. Could someone explain to me, what does it mean for a spring constant to be 20 newtons per meter? What does that mean for the spring? Please, someone. Yes, Gavin.
For every 20 newtons of force, the spring will move 1 meter in displacement?
Yeah, exactly. Every 20 newtons of force you exert on that spring, you'll stretch it 1 meter. That's right, you get 1 meter of stretch for 20 newtons of force. Beautiful. That's what the spring constant 20 newtons per meter means. So now here's what I'm going to do. 1, 2, 3, 4, 5. I'm going to cut the spring in half so that now my spring will only have 5 coils. Okay? My spring only has 5 coils now. Here's my question. What just happened to my spring constant? Did I just cut the spring constant in half? Is it now 10 newtons per meter? Is my new spring constant going to be 20 newtons per meter? That is just unchanged. I cut the spring in half, but the spring constant remains unchanged. Or did the spring constant get doubled to 40 newtons per meter? Please think about that right now, and I'll come back to you in about a minute or 2 minutes. Please think about that.
I would think it'd stay the same because the constant depends on how much force you exert to get you move, and if it's still around the same tightness, then it would double.
Did you guys play around with your springs yesterday?
No.
Never mind.
We did our lab.
You guys didn't play around with it at all, like swing it around or just go boing, 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 boing?
We did our lab.
In the physics lab, you're supposed to have fun. Not be boring like you're a boring white person.
I took chemistry. I get to be boring white person.
But Miss Min's not boring.
Okay, you guys ready to vote? Okay, how many people say the spring constant gets cut in half? It is now 10. 0 of you. How many people say the spring constant remains 20? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. How many people say the spring constant gets doubled to 40? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Wow, this is the only class that doubling the spring constant won. I think it makes sense to me why the spring constant would remain the same. You who voted for this just figured, hey, same spring constant. Who cares if you cut it in half? So the real question is, why did 14 of you vote for double? Yes, Logan.
Because when you need to find k, you divide by x. So if you have a smaller x, you divide it by less.
Okay, so how many people think that by cutting the spring in half, now for a given force, you're going to get less x? Okay. Noel? Well, I gotta tell you, what Logan said is totally correct. It's totally true, and that's the way a spring works. And so now I want to talk about how a spring works. And it works in a similar way that tension works. Do you remember tension, where I told you when you have a spring, a string that's holding up a weight? Let's say I have this string holding up a 10 Newton weight. The only molecule in the string that's holding up the weight is this molecule right there, the molecule in contact with the weight. So this molecule feels 10 newtons down, but because this molecule isn't accelerating to the bottom of to the center of the earth, it must be experiencing 10 newtons up. 10 newtons up from where? The guy directly above it. And so on and so on. So the next guy feels 10 newtons down and 10 newtons up. In fact, every single molecule in this chain of molecules is going to feel 10 newtons down and 10 newtons up. Well, the same thing is happening with this spring. If I hang a 20 Newton weight off the end of this spring, then which of these coils is holding up the 20 Newton weight? Only the first coil. Only this coil is holding up the 20 Newton weight, in the same way that only the first molecule is holding up that 10 Newton weight. So this little coil here has to stretch, and it stretches until it stretches enough to hold a 20 Newton weight. Well, there's 20 newtons down on him, which means there's got to be 20 newtons up on him, which means there's 20 newtons down on this guy, and so this guy's going to have a delta X, as well as this guy, as well as that guy. You see that? Every single coil has to be the same. Every single coil is going to be stretched the same amount, delta X. Alrighty? Well, when I cut my spring in half, I'm just cutting in half the number of coils I have. But this guy here, this guy still has to be delta X. You know? If I've got 20 newtons hanging off of him, then this first coil has to stretch the same amount, no matter how many coils are above it. So, as Logan said, when you cut the spring in half, you cut the displacement in half. So now 20 newtons of force is not getting me 1 meter of stretch. Now what's 20 newtons of force getting me? How much distance of stretch is 20 newtons of force getting me now? Yeah, half a meter, exactly. So now, because 20 newtons of force is only getting me 1/2 a meter of stretch, that makes the spring constant 40 newtons per meter. So yeah, you guys are correct here. Let me demonstrate this even further, okay? Look at this spring. This spring has lots and lots of coils in it, okay? But I'm going to hold this spring at the very bottom so that none of those coils are going to stretch. Only a few coils are going to stretch. And I'm going to hang this 10 Newton weight off the bottom. Do you see how much space there is between these coils? Is that spacing going to change if I greatly increase the number of coils? Look at the spacing. If I greatly increase the number of coils, do you see that the spacing is about the same? That the spacing didn't become significantly bigger like that? Okay? That it doesn't matter whether I hang it here or like that. Do you see how what's below my finger hasn't changed? You see? Or if I, here, let me put it up low. Okay? Okay, so here, I am now going to grab it here. Is the spacing on these coils going to change? Not at all. You see? Because the spacing on the coils is determined by the spacing on the very first coil that has to hold up this 10 Newton weight. And all the other spacings is just gravy. It's just extra stretch. I tore out some of my hair. So I'm hoping that makes sense to you. That what Logan said is true. Cutting the spring in half just for the same force cuts the stretch in half. So what happens to K when you cut the spring in half? What should I write there?
Doubles.
Yeah, it doubles. Now I want to remind you, when you have a large spring constant, when it takes a lot of force to get a stretch, we call that a stiff spring. So the spring got twice as stiff. It's a stiff spring, okay? So generally, if I want a really stiff spring, do I want it to have a lot of coils or very few coils? Yeah, very few coils. Imagine your car's suspension, okay? Have you ever looked where your wheel is? Then you take the wheel off and you can see a shock absorber or a strut, and then you can see a spring, okay? Tell me, how many coils does that spring have, approximately?
Like 6.
Say again?
Like 5 or 6.
Yeah, 5 or 6 or 7, okay? Why? Why would a car's spring suspension have so few coils? Because you want it to be really stiff. You want it to be really hard to compress that spring, because that spring is going to keep your car from bottoming out. You know, you want a stiff suspension. You don't want your car to be going wow, 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 wow. So they've got to give you a spring in your suspension of very few coils. Okay, great. Well, hey, let's do the next one. Here, 2. What happens to K when length of spring is doubled? Hey, you tell me, what's going to happen to the K when I double the length of the spring? Thank you very much, Pooja. We're going to go with Pooja. It's cut in half. It's cut in half. It is now no longer a stiff spring. It is a loose spring. Loose. It is a loose spring. Okay? And then finally, I put an identical spring in parallel to it. Let me get a jiffle on it. I want you to picture this. I've got a spring, and I'm going to hang some weight off of it, like 20 newtons. And then I'm going to put an identical spring in parallel. What's going to happen to the spring constant of this system of springs now? I'll give you 2 choices. It's either doubled or cut in half. Which do you think it is? Are you going to get more stretch for your 20 newtons or less stretch for your 20 newtons? Less stretch for the 20 newtons means it's a stiffer spring, means K is doubled. More stretch means it's a looser spring, K is cut in half. How many people here say, this is going to be a stiffer spring, less stretch, you're going to double your K? Okay, good. I'm just going to leave it there. Someone explain why. Why is it? Yes.
Because the 20 newtons of force is shared between the 2 springs.
Beautiful. Yeah, you're not exerting 20 newtons of force on this spring anymore. You're only exerting 10 newtons of force. It's like Sean said. If I put a second spring in parallel, now I'm only getting 10 newtons of force on each spring. So definitely the stretch of each spring is going to be cut in half. So for a given force, you get half as much stretch. That means you've doubled K. K is doubled. You're going to have a lab where you experience this, but I want you to see what happens here. Look at these 2 guys and look how much stretch I get. This mass is coming here, here to where the ring stand is. But if I hang this guy from only 1 spring, then look how far the mass goes now. the mass almost goes to the stand itself. So for a given force, I'm getting a lot more stretch, which means I'm going to have a much lower, or rather a much, a lower K here. I'm going to have a higher K here, just like Sean said, because this force is being distributed between the two springs now. Okay, well, hey, that's all I needed to say about that. Any questions or comments? Then, hey, let's do a spring potential energy. I'm not going to prove it right now. I'm just going to say it. Spring potential energy, which is equal to PE sub S, spring potential energy, is given by the formula 1/2 kx squared. There it is. So here's a spring. When I compress it, now this spring has a certain amount of spring potential energy. I can realize the spring potential energy by releasing the spring. You see? So for example, let's go ahead and, how am I going to do this? Yeah, let's do it like this. I'll stick my thumb in there. Okay. So here we go. Here's a mass, a 20 gram mass. I'm going to put the 20 gram mass on here, and then I'm going to pull this down. So now there's a certain amount of spring potential energy. When I release this spring, what's going to happen? Yeah, mass is going to go up. That spring potential energy will be converted into kinetic energy. And the mass will go a certain height, which means that spring potential energy will be converted from kinetic energy to gravitational potential energy, just like normal. Here, watch this. 1, 2, 3. You guys okay with that? And you saw how high it got. It got about up to there. Alrighty. Now, what if I put a mass with half the mass? This has half the mass, and I compress this the same amount. Does this mass have any more or less energy than the other one? No, because the energy is with the spring. The spring doesn't care what mass is on top of it. The spring potential energy is just determined by how much you're compressing the spring. But if I let go, what would I expect this lighter mass to do?
Go higher.
Yeah, go higher, right? MGH, if it's got a smaller m, it's going to have a bigger h. Here we go, watch this. Did that go higher?
Yeah.
Yeah, I would have expected twice as high, but it didn't go twice as high. Maybe I should do it differently. Here, what? Oh, stupid thing. Here, just a second. Here, let's see if it goes actually twice as high, which would be predicted by physics. Here we go. Oh, good hands almost. Well, it went higher, definitely, but maybe not twice as high. Last period it hit Carly. I was glad it didn't hit her right in the eyeball. Good thing she was wearing her safety glasses. Okay, so here we go. Conservation of mechanical energy. If the work done by non-conservative forces is equal to 0, then initial mechanical energy equals final mechanical energy. You get conservation of mechanical energy. So now I want to ask you guys, what are all the types of mechanical energy we've learned about? What's that?
I said, oh my God, there are a lot of them.
Sure, tell me one of them.
1/2 mv squared.
Thank you very much, Pooja. 1/2 mv squared. Linear kinetic energy. So we got 1/2 mv squared and 1/2 mv squared here. What's another one?
MGH.
Yeah, MGH. Good. Gravitational potential energy. MGH. MGH. What's another one? We learned it in chapter 8 and 9 rotations exam. Tell me, John Vincent. No, something else. Has all the rotational stuff. Do you remember in rotation land, what do we call it? Mass. It's not mass, it's...
Oh, double.
Good for you, Noel. 1/2 I omega squared. Great. Great. And then finally, now we get to add a fourth term to this, and that's spring potential energy, 1/2 kx squared. Alrighty, so now I'm going to give you some conservation of energy problems, and you've got to decide which of those four, which of those 8 terms are present, and then you'll let her rip. So here comes the first one, and I'm gonna give it like IKEA, instructions from IKEA. There's not going to be any words, it's just going to be symbols. This is frictionless. This is 2 kilograms. Going 5 meters per second towards a spring. A spring whose spring constant is 200 newtons per meter. And it hits the spring. So now my 2 kilogram mass is like this, and the spring is really compressed. Okay. And this 2 kilogram guy is at rest. Alrighty. And I want you to find the maximum displacement of the spring. That is, what's the displacement of the spring when the mass is momentarily at rest? Good luck. I'll give you a hint. Please start with initial mechanical energy equals final mechanical energy. If anyone's having difficulty getting started, I just want to point out, initially, the only type of energy this mass has is kinetic energy. And then when it's momentarily at rest, the only type of energy it has is spring potential energy. That's all it's got. So what'd you guys get for X?
Very low.
Pooja says 0.5. How many people agree with her?
Yeah.
Yay. Any, not a lot of hands. Any questions? You didn't get 0.5? You got 0.5? You remember to take the square root of that thing? Yeah. Okay. Hey, any questions or issues? Before I give you a more interesting one. Okay, hey, here's another one. And I'm going to walk around and help you on this one. This is example number 2. Now I've got, here's a 0.5 kilogram mass on a compressed spring. The spring constant of this spring is 200 newtons per meter, and the amount it's compressed is 0.8 meters, 0.80 meters. So I'll call this 0.50 kilograms. Are you guys okay that this is a mass resting on a compressed spring? .5 meters above this mass is a ceiling. I'm going to release the spring, just like I demonstrated with you with my little spring, okay? So release the spring. And now what's going to happen is this mass is going to fly up and hit the ceiling. And I want you to find what speed I hit the ceiling. Okay? With what speed do I hit the ceiling? The ceiling is initially 2.5 meters above the height of the mass. I'll give you a hint. Please do initial mechanical energy equals final mechanical energy. Good luck. This is the initial state, that's the final state. I'll give you a few seconds and then I'll walk around and help you.
So then I don't need the MGH for it and that 1/2 square.
There you go.
With the MGH, the situation will be the 1/2.
Well, you tell me. Finally, the final situation is the mass slamming into the ceiling. So what kinds of energy does it have?
Oh,
It has a speed when it hits it.
oh, okay.
I see what you got. Okay. You're totally correct, except it's also 2.5 meters above its original starting place. So it's gained some gravitational potential energy as well. Now, if we define the initial state as 0, you can say it starts with no gravitation.
Square
B squared.
D is squared.
No, it's in the final condition. Yeah, initially, all it has is frame projection. No, you put a positive.
Okay, there we go.
Don't ever put a negative charge in kx. Or in this case, 1/2 kx squared. So, you know, since we're pointing squares, I guess it's very negative, but it gets squared.
The spring is recovered.
Good. So you got kinetic, you're gonna put gravitational potential on the right side of the equation. Well, go ahead. Initially, what kind of energy does it have? And at the end, what kind of energy? Okay, what you're doing is correct.
This?
Plug in and you win.
It doesn't really have, it's like,
This is good.
You know what it is?
No, this should be 1/2
you know what that
mv
is?
squared.
Yeah, okay. It doesn't really have a flavor, it's just like a combination.
I mean, 0.5 times v squared. Rob, what you're doing is totally correct. If you punchy correctly, you win. What did you get? Here's the thing, oops, sorry. initially you have spring potential energy. That's the only type of energy you have. Wait. Oh, this is what's the other problem? Okay. Initially, all you have is spring potential energy. So initially, all you got is 1/2 kx squared. When it hits the ceiling, at that point, it's got gravitational potential energy and kinetic energy. So the left side of your equation should be spring, and the right side should be gravity and. Okay, that's good, but you should have plus mgh. You forgot the gravitational potential energy. Let me see what you got, please.
I forgot to square.
Okay, good, because what I'm looking at looks correct.
14.3.
Okay, so you got mgh.
I can't round. So.
Okay, look at your kinetic energy. I'm sorry, your kinetic energy on the right. That should be 1/2 times 0.5 times v squared. It's 1/2 mv squared. Oh, there it is.
5 times.
Oh, well, something went horribly wrong with your math. Oh, did you remember to square the 0.8?
Square 0.8.
Yeah.
What's the answer?
14.4.
Oh!
We all have it.
So you got your spring, your kinetic. Yeah, if you do the punchy correct, you win.
Good job, Quincy.
Oh, you're so smart, Noel. Don't ever change. Okay, can I see? So you've got on the left side 1/2 kx squared, yay. On the right side 1/2 mv squared and mgh. Okay, great. That's going to work out for you. But you're writing so microscopically, I hope you don't mess up. What the heck? Oh my God. Okay. What you have here, this is mgh. Okay, what you have here is correct if you solve it that way. Okay, man, so the answer is 14.4. I'm so sorry we ran out of time. But this is what you should be looking at. At the very least, write this down. This is what you should be having. Your spring potential energy is equal to the sum of those two. Okay, bye-bye.